All right, here we go. Welcome to another exciting day here at Spain Park AP Chemistry. Today is Friday. Oh, thank God it's Friday. And the date is February the 22nd. 23rd, how time flies. 2024. We're going to be working on the 3 different types of ways to calculate the equilibrium constant K. We did yesterday, we went through and they just give you everything, but the second one is going to be like number 35 here on page 663. So when we look at this, the first thing we have is our equation. So what would our equilibrium expression look like? Everybody take 30 seconds. Write your equilibrium expression for that. You can do it on the back of your notes if you want to. That's why I only did one-sided on your notes. Do you need to do the other one?
No, I think I did it.
Okay.
This doesn't look good.
Oh yeah, okay. But 3 compared to week is it's 2 now. It's 2 still. Yeah. It's like a really obscure app. It only has like 53 reviews. Why? I mean, I see why I'm using it, but I don't know why. We're still being purchasing supply on that day.
Okay. We got to have this flowing in the background while we do this. So, what's my equilibrium expression going to be?
K equals
So KC,
the concentration of N2.
concentration of N2, and Hill is answering this.
Okay.
H2O. Now, what do I need to make sure?
It's not a liquid.
It's not a liquid, because only aqueous and gases. Okay? This song is going to go on for long enough for us to be able to finish this whole problem. Okay? Over what, Hill? NO to the second. Okay? Squared. Right?
Yes.
So now if I write this equation, so I'm going to say 2NO plus 2H2 goes to N2 plus 2H2O. Alright? This is where ice baby is going to come in. Because we are going to make an ice table. I just can't, I'm really struggling because I want to break it down right now. So, yeah, something might break. Yeah. It gives a whole new meaning to breaking it down. Something might just give away. So I have 0.1 mole of NO initially, 0.10, and it's in 1 liter, so it's 0.10 molar. I have 0.050 moles of H2, but it's in 1 liter, so it's molarity, and 0.1 mole of H2O. So I have 0.10 molar of that. How much N2 is placed into it?
I don't know.
0. Did they put any in there?
Oh.
They just put those 3 in, right?
Wait, so why is N2
Why is what?
Why is it there?
It's 0.
Because that doesn't mean it's not going to get made. They just didn't put that into the container.
Oh, for the.
For the reaction to go, they just put these 3 things in. Okay, it's still part of the reaction, but somebody went and put these 3 things into the container to make them react. Okay? So, what's the only way this reaction can go initially? It can go both ways, but which way is the only way it can go? It can only go to the right, correct? But is it going to go completely to the right?
No.
Because it's at equilibrium. Oh, you thought it was over?
Is it on loop?
No.
Is it gonna end?
At some point it ends.
I just wanna make sure you don't wanna.
No.
Go, and I
Okay.
can start it.
So here's the deal. So initial, how much of it's going to change? Well, we don't really know, but it does tell us that at equilibrium, the NO is 0.062. At equilibrium, the NO, now you can go turn it off. Okay? Is 0.062 molar. Okay? Yeah, just close out of the whole thing. Alright, so initially we're here. This is what got put in initially. And at equilibrium it says that we have 0.062. So how much of this must have reacted to get to 0.062?
How much of both of them?
No.
4. 0.
If we start with 0.1 and we end with 0.062, how much must have reacted?
0.038.
0.038. So minus 0.038 is my change. So we have an ice, initial, change, equilibrium. Ice, ice, baby. Initial, change, equilibrium. So initially, I have this. I'm given initial concentrations and 1 equilibrium concentration. Okay? But stoichiometrically, we can figure out the rest. For every 2 of these, how many of these reacted? 2. So if 0.038 of this reacted, how much of this must have reacted?
Same.
The same amount. 2 reacts with 2, so this is going to be minus 0.038. So 0.05 minus 0.038 leaves me how much in equilibrium? 0.012. Yells great math. 0.012. That's my equilibrium concentration, because however much of this reacts, the same amount, it's a 2-to-2 ratio. So I know that 0.038 of this, so 0.038 of that must have reacted. So now, for every 2 of these, how many of those got made?
1.
1.
So half.
So half of what?
0.038.
So this is going to be plus 0.019. So at equilibrium, I'm going to have 0.019 molar. And what about this one?
Plus 0.038.
Plus 0.038. Correct? So what's my equilibrium concentration going to be? 0.138. So now I know my 3 equilibrium concentrations. So in a sense, they're still giving you the equilibrium concentrations, just not directly. Here, they just give it to you directly. Here, they're making you work for it just a little bit. Okay? I love our AO system. I love it. Yeah. Just you sit right back in the corner here. I'll be back. Hey, dig through it's on the right there on the corner. Which ones do you need to do? The equations or the naming? Okay, so equations test is I think right there. Alright, so now the last part says calculate KC. Well, how do we calculate KC? Well, KC is equal to this, right? Now we just plug it in, So N2, your equilibrium is 0.019 times the H2O, which is 0.138 squared, divided by the NO, 0.062 squared, times 0.012 squared. Okay? So figure out what that's going to be.
Such a productive game.
Just back in the corner back there.
We don't talk about that.
And then figures and answer the questions that we have to download online. No. Dude, also, I know. It's required by the state. That's so useful. Why do we gotta get this? Why do we need it?
Yeah, in a second. All right. So on this type of problem, you're given the initial concentrations and one equilibrium. But from that, from the stoichiometry and the coefficients, you can figure out what the change is. Now, how did we know it had to go to the right again?
Because there wasn't any N2.
Because there's none of this for it to react with at the start. Okay? So whichever side has 0, then we know it's going to go that way. Now, there is going to be a little add-on here where we're going to learn how, if they give you all 4 of them, we're going to have to figure out a different way to know which way it's going to go to reach equilibrium. That's going to be a Monday issue. All right, so let's look at now number 36. 36 says we have H2 gas plus Br2 gas goes to 2HBr gas. But this time it says that the mixture is 1.374 grams in 2 liters. And the bromine is 70.31 grams in 2 liters. What doesn't he have? He doesn't need an answer key. That's what he needs, his notes, and he needs to figure out the answers. We don't just copy the answers. Okay?
This wasn't the naming, or the equations one.
The math one's not the naming one. I mean, that equation one's the naming one. How do we what do we need to do to that first?
Go to molar mass, or moles. Go to moles. Where do you get a molarity?
Yeah. How are you gonna get to molarity without your molar mass?
What do we have to do first?
Go to moles.
Change it to molarity. Because Kc is always in terms of molarity. Okay? So how do we change this to the molarity of the H2?
Molar mass.
Okay? I gotta take 1.374 grams. Hopefully we know what's the molar mass of H2. 2.02 times 1 mole over 2.02 grams divided by 2 liters. Is it 2.0, 2.00? Get another sig fig in there, so we got 3 sig figs. Some of y'all really on sig figs on this test. Just kind of forgot about it completely. So the BR2 is going to equal bromine 79.9 times 2 is going to equal 159.8. So the first thing we have to do is just get it in terms of molarity. And so I know somebody's doing these numbers for me.
For the BR2, I got 0.22 moles.
0.22. But how many sig figs is everything given in?
It's 4, but it's 0.21999.
So that doesn't mean we don't have a last digit. It's just going to be a 0 there. So that's going to be that molarity. What's the top one? 0.170 molar H2. Okay, so now that's just an initial step to get our initial concentrations. Okay. Now, at equilibrium, it's found to contain 0.566 grams. So what are we going to have to do with that? So this is initial. Okay. So the H2 at equilibrium is going to be do the exact same thing, 0.566. What do we know? Wait, 566 grams of what? H2. Times 1 mole over the 2.02 grams. Divided by still in 2 liters. I mean, you can subtract the difference and just, convert that. That's going to be your change, but I think it's easier just to do everything in terms of molarity.
I think the 0.17 isn't the right number.
Yeah,
It's not.
I got 0.340.
Point what?
340.
It just got divided by 2 again.
Okay. And this bottom number, y'all, when you disagree with the number, you got to let me know.
0.140.
0.140 molar. So now we end up going and having to do our ice table. Okay? So I'm going to rewrite this. There's not enough room right here, so I'm going to rewrite H2 gas plus Br2 gas 2 HBr gas. Now look, a lot of teachers make their students just do a whole new table and just kind of do everything out. To me, it's a lot easier just to do it around the equation itself, okay? But you need to do your initial, your change, and your equilibrium. So I know my initial H2 is 0.34. Let me do it a different color just to make it stand out. 0.34 molar. I know my Br2 is equal to 0.22. 0 molar. I have 0 of that to start with. Then it tells me at equilibrium I have 0.140 molar of that. You finish it from there. calculating pleasures. Also, I'm just gonna tell you on Monday, I'm gonna look at all of your kinetics problems and give you a classwork grade for all of your kinetics problems. So between now and Monday, get all of your kinetics AP practice problems together.
I'm making a sheet. Yeah. Just target this stuff.
Coach Hall? Who's yours? Paula. Paula? Paul and Paula.
Yes. Yo, I need. Bro, just instituted something I didn't even do. No, I don't want to hear you say you're making a move or something, bro. Remember when he.
Right, remember when we were working on these problems?
Oh, I'm done. Actually, I never finished it. I didn't finish it. Hey, you don't just stop.
You know, most people don't.
Yeah, it is.
All right, so based upon the noise, that means we're close to being done.
Yeah.
So if we go from 0.34 to 0.14, what's my change?
Minus 0.2.
Minus 0.2. Okay, so this one's going to be minus 0.2 as well because it's 1 to 1. So that's going to make this one equal to 0.020, right? So almost none of that left. And then this is going to be plus, is it 0.2?
0.4.
0.4 because of the 2. So it's going to be plus 0.4 molar. Does everybody understand and see that ice table? That's the most important part of doing this type of problem, is your initial change in equilibrium. No, they already have them all. They already have them all. That's just for the next class. I just didn't have time to, yeah, they can just go right there on that corner. All right, so if I'm going to do KC, KC is going to equal 0.4 molar. What do I have to do to it? Square it, divided by 0.14 times 0.020. And what does that turn out to equal?
57.1.
I would say 2 sig figs because, well, this really should be 3 sig figs everywhere.
So it's 57.
57.1. Okay? Because it's 3 sig figs throughout everything with the zeros. All right, so that's the second type of equilibrium problem. You're given initial concentrations and one of the final concentrations, and you need to be able to calculate all of the concentrations at equilibrium, then calculate the value of K. Obviously, if you're asked to calculate the equilibrium constant K, you have to know all of your equilibrium concentrations. You can't have two variables. So there's got to be a way to figure it out. So the third one now, the third one is going to be on the packet that I just gave to you. We can look at number 1988. the very first page. Well, there's more current ones, but this one gives the third type. Okay? So let's look at this and let's work through, and I want to get to part B because part B is going to be the third one. And for your notes purposes, let me go ahead and write that out. The third one is you are given an initial concentration of reactants and a percent reacted. Okay? And a percent reacted. So if I look at A, all right, what is the concentration in moles per liter of SbCl5 before any decomposition occurs? Well, we can do that, right?
Yes.
So how do I do that one?
Go to molarity.
Well, just find the molarity, just like we just did, right? So take a second and do that, and then what about number 2? What is the pressure? How would I find the pressure of the gas before we did any decomposition?
P equals molarity times RT.
Okay, the ideal gas law, which we can end up doing, pressure is equal to MRT, or you can just use PV equals nRT, and because you have some of that there, however you want to do it. So do those two things. Ooh. This period has been so messed up that it's almost over already. Now, Bennett, you need help. He can help you. Okay? So you just can't copy a key, but he'll be glad to help you.
Ideal gas constant like 0.0821.
Yes.
Yes.
All right, because time is short and we theoretically already know how to do these, I want to just go ahead and do these out. Okay, so the molarity is going to equal 89.7 grams divided by, they tell you the molar mass, 299.0 grams per mole. That's my moles divided by 15 liters. And that's going to equal, what, did anybody get a number yet?
0.02.
Okay, one person say it loud.
0.02.
Exactly? Okay, so I'm going to go 002 molar. Okay? 3 sig figs. Now the pressure, okay? The pressure can be MRT. So it can equal 0.0200 times 0.0821 times the temperature of 182, but what unit must that be in?
Kelvin.
Which is equal to
455.
455K. I'm cramming that in. So the pressure just turns out to equal
0.747 atmospheres.
0.747 ATMs. Okay, so that's how they throw in ideal gas law. They just throw it in there, just randomly. Okay, to be honest with you, that's about the most a gas law shows up. It's just kind of like that. Okay, so that should be easy money. But now we have, so I have my initial concentration is 0.0200 molar. 0 and 0 of these. Right?
Yes.
But do I know anything? It says if SbCl5 is 29.2% decomposed, so how much is going to change?
Minus 29.2%.
So it's going to be minus, and to multiply by 29.2%, I should have to remind you of this, but what do?
0.292.
Move the decimal 2 places, right? So it's 0.292 it's gonna be minus 0.292 times 0.0200. So that's gonna come out to 0.0584.
That's 0, 0.
0.00584 molar is my change. Right? Is everybody with me? So when you subtract that out, that turns out to equal 0.01422. Okay, now this is going to be plus 0.00584, and this is plus 0.00584. Now look, it starts at 0, it's got to be 1 to 1. You can put it in here and then write it down again, but the whole point is just kind of keeping track. So we want to save time. So when you're doing your ICE table, you know that this is going to be plus and plus. You can save time. Now again, if you need to for organizational purposes or because of your OCD, you can go ahead and put in your 0.00 whatever here and 0.00 whatever here, and then rewrite it again right there. Now if there's something above it, I recommend you go ahead and do that. Now let me finish the thought and then I'll answer your question. Once you have this, now what do we do?
Plug it back in.
Now you just plug it into your equilibrium expression. Now look, we can calculate for Kp or Kc. If we wanted to do Kp, you start with your initial pressure. Okay? 29.2% of the pressure. And do everything from that. And then you just plug it into Kp, and then you put the, remember Kp is going to equal the pressure of SbCl3 times the pressure of the Cl2 divided by the pressure of the SbCl5. You just put the pressure values in. Either one, you just have to identify. Layla.
What's the number next to 0?
0.02. Did you stop it?
Did you not stop it?